Hi, I'm Dean. This is Michaela, and we did our indie lab on Michaela's dive. She's a good swimmer, so we figured we'd investigate some parts of her dive that make her such a good swimmer. Our presentation is going to hopefully begin with this YouTube video.
Our entire lab is based off this
and
one.
Adios to that. Hold on. We're gonna watch this YouTube video. This is a video of Michaela diving in slow motion.
Full screen.
Full screen, full screen.
There we go. Beautiful dive. Awesome. So, this is the boring stuff, the setup. The purpose of this lab was to investigate which parts of her dive made her dive so good. And we sort of hypothesized that by looking at this, making simulations of her dive, we'd be able to figure that out. And then from those simulations, we hypothesized that the movement of her legs, her arms, and her back, or her torso area, would add up about equally to create the total rotation that she gets when she dives, because obviously you start in an upright position on the diving board, obviously not like this, and then you go to a down position. So we were trying to figure out exactly which movements created that rotation. This is our diagram. This is sort of just a basic dive. You can do it at different angles, and you can see that in that pink one, they start off, that's the one that models her most closely. They start off pretty low, but upright generally, and then they go to a more downright position. To take data for this lab, we just recorded Michaela diving. We did it 5 times with a slow-mo camera, and we chose the best video of the 5 to analyze because we were doing so much analyzation. It would be just an enormous amount of work to do all 5 videos, and we figured they were all pretty much the same. So we just chose the one that worked the best and looked the nicest to analyze, because you don't want to analyze a crummy dive, because then you just do crummy things off. So the background, we used the equations for rotational kinetic energy and moment of inertia, which goes into the rotational kinetic energy, and that's where a whole bunch of our math comes from. And Michaela's going to take over with the data explanation and everything.
Okay, we have 3 slides of data. So this is our leg data, and what we did is we, in video analysis, we dotted every 3 frames, my ankle, then we did my hip, and then we did my shoulder and my elbow and my wrist. And we did the shoulder twice and the hip twice, so we could get the leg and then the torso. And then the arm, we did 3 joints, because when I do the dive, it's not completely straight. I don't straighten out till the very last second, so we figured it'd look like this, and it would just be weird. So yeah, this is all our crazy data for legs and arms, and we got the average, and how do we do that again?
We just added up, we used the Pythagorean theorem to find the length of her leg, and we found the length, and then we averaged the length to get data for the equations in our background so that we can use those.
What does that average mean then?
It's the average length of her leg or torso or arm segments as she goes through her dive, because you need the length to do moment of inertia calculations, and because of the way we were dotting it, it wasn't exactly the same length every time, so it varied, I don't know, in the 3rd decimal point, 2nd decimal point a little, and so we had to take an average of that to find the average length of her arm through our calculations.
And then this is our torso data, which is the arm and leg data, and then we did a full body average, so we did it from my shoulder to my ankle, and we kind of compared that with the rest of the values we got. And then we found this cool website, or Dean did, that had body proportions, so we could kind of line them up with how my lengths were and my arms and stuff to make sure we were correct.
And specifically, we got a whole bunch of mass data, so that had percentages of how much your arms weigh compared to the rest of your body, and that's how we did all of our mass calculations, instead of having Michaela put her arm on a scale, because that would be weird.
That'd be hard to measure a leg, because you'd probably get other mass too, and so we just did that. So we had a main data table, so we kind of shortened all our data down into this, and then we had the moment of inertia and rotational kinetic energy, and yeah, and then we had my stats. And we have more data of how we did the next slide, which we made animations, but it was so incredibly long and like repetitive that we didn't put it in here. But so we made animations for each part of my body. So this is my elbow, and then my wrist and my shoulder, and we did it by frames, and so we were able to get it to move. And then there's my torso, and we only did one of my legs, and then we did our full body, or my full body average, and then we put them all together and created this. And it's kind of interesting because at the very end, it goes up to 9 frames. I'm not in a straight line, which makes sense because I don't straighten out until half of my body is like submerged. Like when I do the dive, I'm like kind of bent and like in all weird contortions, and so that's why it's not straightened. So yeah. Do you want to do the graphs?
Yeah. So these are graphs of all of our data that we use to do calculations with. Obviously, this isn't all the position data for her tracking that we used to do the animations. This is the data that came from that. So in the previous slide, you saw a whole bunch of lines that were rotating around each other, and we compared the heights of the 2 points to get a change in theta in radians, and then we used that to find the angular speed of her rotation, which we converted into rotational kinetic energy using her moment of inertia calculation, which we did a few slides ago also. So these are the graphs of her angle, the change in her angle versus time. So we got the slope of that to be angular speed. We used that angular speed calculation, or number, to do calculations on rotational kinetic energy, and this is just that. And our hypothesis for this was that the 3 would essentially add together for legs, torso, and arms to get the full body approximation. But we found that with the arm thing, since there were 3 joints, we couldn't do the calculation in the same way, and we couldn't figure it out at all, which was really shocking to us, and we don't know how. But yeah, it totally stumped us, and so we had to just say, we don't know how to do this. It was too complex a system, and the whole point of the lab was to simplify the system, so we were really disappointed that we couldn't figure that out. But these are the graphs of those, and we got the slopes from those. We took them out. You can make the next slide,
Mm-hmm.
so this is our error. Our experimental value was adding the leg and torso data together to find the total rotational kinetic energy of that, and our accepted value was the total rotational kinetic energy of her full body approximation animation. And we were off by about 38%, which was like, oh my gosh, 38%. But then we reconcile that with the fact that we were unable to put the arm rotation in because it was so funky, and we were assuming that it was going to be about a third of that anyway. So a huge chunk of that is coming from the fact that we don't have the data for the arms because we just couldn't figure it out. So in reality, it would be more like 5%, we assume, because there's something that we're missing in there that's causing that error.
And that adding the arm would increase your experimental value? Is that what you're saying?
Yeah, so the experimental value was the rotational kinetic energy of the legs, which is about 1.7 joules, and then the rotational kinetic energy of the torso, which was about 0.4, and we got that number there. And so we assumed that the arms would be about a third of it, and if you subtract those two, you get that the arms are about 1.3 joules, and so we'll talk about that later in our conclusion, but we're assuming that that arm data is a huge piece of the puzzle that we're missing, and that makes up for a lot of the error that we're missing, that we have with this.
And, sorry.
Oh yeah, sorry. Some other sources of error were that we were dotting on the computer, and obviously that's hard. We made mistakes, and you can see that in our full body conglomerate animation where the hips are like 2 joints and they're like there and they move apart. So we had some error in the placement of our dots because we didn't like draw a circle on her hip or something, which could have been done and to improve our error.
But when like analyzing it, it was a very blurry video, and like each frame you couldn't get the exact spot that you did the last time. And so like in the full body thing, we did the shoulder twice because we did the arm, and then we did the hip twice because the torso, then the leg. And so in the full one, we kept both of those in there to see how they lined up. And so they're a little off, which means that's part of our error.
So our conclusions were pretty neat. The first one was that the rotation was essentially as we predicted. It was caused mostly by the movement of the arms, legs, and torso. But on top of that, we assumed that the legs and arms were doing most of the work. The torso ended up looking more like a byproduct of the movement of those two, which was interesting because we initially predicted that they would be about equal. So it was nice to see that the legs moving did more than the torso, which in hindsight makes sense because the legs are bigger, they have longer length, they have more mass per each. It's about half of the mass of your body, I think, just your legs. And so those contributed most, about half each we assumed. We couldn't get specific data for the arms, so we had to make that assumption, which was uncomfortable for us, but we wanted to have the lab feel whole, so we put that in there with the state, like just recognizing that this isn't actual data that we have, so we can't say for sure that's what it was. The other thing that we found out was that simulations are a really fun and cool way to do labs because it makes a really complicated movement that has many pieces to it more simple to analyze. So we were able to take a huge dive, which has all these different movements in it, break it up into little pieces, look at those pieces in a dynamic way, and make what we think valid conclusions about how those movements affect the movement as a whole. So that was our lab.
Neat. Thank you. Time for one question?
Ben?
Could you go back to your graph slide?
Yeah.
We'll go back.
Can you explain why the graph of theta versus time for full body approximation's shape is so different than the one for the torso one, and also why you put a linear fit on the torso one?
Yeah, so that was actually something that I should have said earlier, and I was planning on it. The torso was weird because at first it had two phases essentially, and there's this upward phase where it's rotating like this, and then there's the downward phase where it's rotating like that again. And we thought about looking at both, but then realized that overall the average of that would be the total rotation that it did. So it takes away from the system when it rotates up and adds back to the system when it rotates down. And so we were able to take this linear fit that way, which is an approximation of the average of that total movement that the torso is doing throughout the dive. And that's why we had a linear fit on it as opposed to some quadratic fit, because we were thinking that overall it's going to have tend towards an upwards motion or a downwards motion. And we found that it was a downwards motion. It was a tiny, tiny motion downwards because of the upwards that it had before. And so that's why we have a weird shape for that graph and a linear fit on it.
Okay, so that would be like the same as like putting a linear fit on this part and a linear fit on this part and then like averaging them.
We had a graph that was that way, but it was confusing to look at because there were so many lines and boxes going on. So we simplified it down to this one. So we did look at both, and we thought about including that, but we decided it was going to be too confusing.
That makes sense.
It was super interesting too, because while analyzing like the hip and doing the dots, a lot of the times the body parts would move, but for a while it was a straight line. Like from when I started until a moment, like it was in a straight line, and like the shoulder would move, so it would look like that. So that probably has some impact on that too.
Yeah.
Awesome. Thank you, guys.